Good morning, good evening, and good night to all of the people who are watching our video. We are students from FTKE of UTeM, and I'm here to start the presentation of our research on transformers for solar PV integration. First of all, we identify two different types of transformers that are used in the integration of solar PV system. The first is the collector transformer. It is a step-up transformer used as a connection point for all the inverters, or in our case, solar panels. Second, the main topic of our research, the distribution transformer. It is a type of step-down transformer that reduces high voltage levels, so the electricity is safe to use. Next, I'm going to talk about the safety standards according to IEEE STD 1547. First, instantaneous power must be monitored at the point of common coupling. In our case, the point of common coupling is the point where the solar panels connect to the grid or a network. The monitoring must be done to prevent reverse power flow, which can damage the equipment. Next, maintaining minimal import at the point of common coupling. This means that minimal amount of power flow into the local network or loads must be maintained. Next, safety precautions such as network protectors should not be interfered by any distributed energy resources, in our case, solar panels.
Hi, my name is Clarice Han. My matrix number is D1124100077. Now I'll be presenting about literature review. Harmonic currents from solar PV inverters increase eddy current losses and cause localized heating in distribution transformers. Low-order harmonics such as the fifth and seventh distort current waveforms and raise winding temperatures. Since winding losses account for 60 to 80% of total losses, these effects accelerate isolation, aging, and reduce allowable loading. This shows that 50 Hz based transformer designs are inadequate, supporting derating practices in IEEE standard C57.110 and compliance with IEEE standard 1547.
At the input stage, the solar power generation system converts the direct current generated by the photovoltaic panels into alternating current, DC to AC, usually at a medium voltage like 400 volt. At this stage, the current may still fluctuate and cannot be directly connected to the grid. So here is where the transformer do voltage conversion. The working principle of transformer is based on Faraday's law of electromagnetic induction. When alternating current flows through the primary winding of the transformer, it creates a changing magnetic field within the core. This changing magnetic field induces current in the secondary winding. By adjusting the turns ratio between the primary and secondary windings, the transformer can modify the output voltage. For instance, if the primary winding has 100 turns and the secondary winding has 50 turns, the output voltage will be half of the input voltage. Simultaneously with the voltage conversion, the transformer also affects the magnitude of the current. According to the power formula, P equals to V times I, there is an inverse relationship between voltage and current. If the voltage decreases, the current increases, and vice versa. This characteristic is crucial for regulating electrical energy transmission. And lastly, at the output stage, after adjustment by the transformer, the voltage and current are optimized to meet the requirements of the grid or specific loads. Ultimately, the electrical energy can be safely fed into the grid or supplied for use.
Next, I'm going to talk about engineering calculation. We created a scenario at which a grid-connected solar PV plant is connected to a 1000 kVA 415 volt / 11 kV oil-filled distribution transformer. The goal of our calculation is to find out how much the transformer has derated from the rated transformer kVA. As we know, transformers have internal power losses that can be found through calculation using equivalent circuit. But according to IEEE C57, the typical ratio of core loss and copper loss was given for typical distribution transformer, which is 0.2 to 0.3. In our case, we use 0.25 as it is the average. As explained previously, the solar panels are a type of inverters and it is a non-linear load. This means that the output of the inverters will be affected by harmonics. The harmonics will cause kVA to derate and transformer to heat up. And based on IEEE 519 and IEEE 61000, the harmonic distortion of input can be discovered. Here we can see the effect of harmonic to the RMS current of inverter output. Now, harmonic loss factor can be found using the ratio of RMS current of harmonic and RMS current of fundamental frequency. Next, we can find out the percentage at which the transformer has derated. Here it is represented as beta max, as in maximum percentage of duration of kVA. Next, we found out that the IEEE standard of continuous loading limits are around 90% to 95%. So using the maximum percentage, we can find out the least amount of derating that can happen to a transformer.
Saskatoon's Dundonald Avenue Solar Farm is the city's largest project for clean municipal energy. This 14-acre site generates enough electricity to power about 435 homes every single year. This location was picked for a reason. It gets amazing sunlight and sits right next to the existing power grid, which keeps construction costs and energy losses low. So, how does it work? Thousands of panels soak up the sun and create DC electricity. But since our homes use AC, we use inverters to switch it over. At that point, the voltage is still too weak to travel far. That is where the step-up transformer comes in. It boosts the voltage up to 34.5 kilovolts, so the power can zip through the grid efficiently and safely. It's a win for everyone, cutting nearly 20,000 tons of carbon dioxide while proving that smart tech can build a sustainable future.
Now I will be presenting about sustainability and environmental impact. Distribution transformers in solar PV systems enable efficient bidirectional power flow, supporting SDG 7 by delivering more clean energy and reducing fossil fuel use. Challenges like harmonic currents and thermal stress can shorten transformer life, but proper design and environmentally friendly insulating fluids help extend lifespan and reduce environmental impact, making transformers key to sustainable energy.
Conclusion, distribution transformer play a vital role in integrating grid-connected solar PV system into the power network. They ensure that electricity generated from solar panel is delivered safely, efficiently and reliably to the utility grid and to us as an end user.